So we've talked a lot about series and parallel capacitors and simplifying them, and we've introduced a lot of equations about capacitors. But now we're going to introduce a few more equations. The first we're going to introduce is energy density. So we have a capacitor, which is two parallel plates. And I drew in a previous video that there's an electric field between the two capacitive plates. So there must be energy in there. Energy density is the energy per unit volume between the capacitor plates. So this is like saying energy in joules divided by meters cubed is equal to energy density. So energy density is joules per meter cubed. It's energy relative to the volume. And the equation for solving for energy density is equal to 1/2 sigma naught times E, or the electric field squared. Sigma naught we know is equal to 8.85 times 10 to the negative 12. So this is energy density, which is energy per volume. But what is just the energy in general, not counting on the volume? Energy stored in the capacitor of joules is equal to 1/2 the capacitance times the voltage across the capacitor squared. So we introduce this equation, Q equals CV. And there's all these different equations to solve for energy. And they are all just taking this equation right here and messing with this formula. So let's say you just have charge and voltage. You can solve this equation not knowing C because you solve for C in this equation. So I'm not going to give you all the energy equations, but I'm going to let you know that using these two equations you can derive all of them. Now, we mentioned sigma R, which is dielectric constant, earlier. My book calls it K, but we called K 9 times 10 to the 9 earlier, so I'm not going to use that because it'd be confusing to have two different variables with the same name meaning two different things. So let's say we have a capacitor with no dielectric in between it, so there's either vacuum or air. I mentioned earlier that the dielectric constant of a vacuum or air filled capacitor is 1. So let's say we put some material in the capacitor, and that changes the capacitance. So if we know what the capacitance is just with air before we add the dielectric, we can solve for the new capacitance this way. The new capacitance is equal to the new dielectric constant times the old capacitance if the capacitor is just filled with air or vacuum. We can solve for capacitance just in general this way. Dielectric constant times sigma naught, which is this, times area over distance between the capacitor plates. This can also be used with charge. The new charge is equal to the dielectric constant times the old charge without the dielectric in between it. The old charge if the capacitor is just filled with air or is a vacuum. And we also can solve for the electric field in the capacitor. So the new electric field in the capacitor is equal to the old electric field if the capacitor is just filled with air or vacuum divided by the dielectric constant. So all these equations tell us what the new capacitance or the new charge and the new electric field is going to be if we add a dielectric other than air or vacuum. A dielectric is just something we put in the capacitor that changes the capacitance.